Okay, in this lesson we're going to continue our work with rational expressions made out of fractions. These, in this lesson, are called complex fractions, and if you look at our example here, it's pretty obvious why they're called complex, right? There's a lot going on here. Fortunately, they follow the exact same rules as we would use if they were just plain old baby pre-algebra fractions. So here is a complex fraction. I'm going to give you a second to simplify it, so pause the video, try that now, and then we'll talk about our strategy here. All right, so there's my solution, and I don't think if you were doing this yourself you would need to show all these steps, but I showed these steps in a particular way for a particular reason. And that's really just to illustrate how we go about solving our big boy pre-calculus version of this problem, right? So obviously here I got a common denominator on the top and bottom, and then subtracted each individually. So we're going to make some annotations about how I did this. The first annotation is we're going to say we simplified the top and bottom separate, right? And then once we had it simplified, what we did, right, is we rewrote our division problem as multiplying by the reciprocal. So as we know, fractions really represent division. To divide fractions, we flip the bottom, multiply by its reciprocal. And then, this is probably the only spot where you did something a little bit differently. I bet none of you did this on your own. So what I did here is I factored, and it canceled out my 3 over 3. 3 over 3 is 1. And the reason I'd want to do that, right, is then I would get a simpler multiplication problem here, which doesn't really matter when we're doing 9 times 13, but it might matter down here when we're using our rational expressions, right? So that's a strategy we're going to use as we solve some of the big boy problems. So I wanted to try it out here as well. So really all we're doing here is we're PEMDASing, right? I'm treating the top and bottom as parentheses and then adding across, and then I'm doing my division and I'm simplifying. We're going to do the same thing here for my algebraic example. So I'm going to start by rewriting my fractions using their common denominator. So on the bottom I can make 15x my common denominator. And same thing, we're just using our funny forms of 1. So on top, and then on the bottom, and then I just start to simplify, right? So I get 5 minus x over 5 over, let's see, if I distribute and then add, I get x squared minus 8x plus 15 over 15x. And then here's where I'm going to rewrite it, right? So I've kind of simplified the top and bottom. I'm going to rewrite it now as my numerator times the reciprocal of the denominator. And I'm going to use parentheses around my expressions to show that we're multiplying, just so we're clear. And notice this polynomial here is factorable. I can factor that as x minus 5, x minus 3, right? So when I rewrite this now, I'm going to say 5 minus x times 15x all over the product of the bottom, and I'm going to use that simplified version. Now, from there, what I notice, right, is that 15 over 5 is 3, right? So I can rewrite this now as 3x times 5 minus x. So just some simplification there. And I seem to be done, right? It kind of looks like I have nothing left that is in common in the top and bottom. But I do notice that I have two things that are pretty close. I have a 5 minus x and an x minus 5. Now, they're not the same. They don't directly cancel. But what I know, and what you probably know too, is that if I wrote something like negative x minus 5 and then distributed this negative across, I would get negative x plus 5, which is equivalent to x minus 5, right? So by factoring out a negative 1, I can actually simplify this further. So that's what I'm going to do here. I'm going to pull the negative out, put it in front, and then that allows me to rewrite this term as x minus 5, which appears in the denominator. And then I can simplify even a little bit further. So that's a little trick we use to simplify these. It's the same as we did with our 9 up on top in our numeric example. We turned it into a 3 times 3 just to make our life a little bit easier. That's what I did here. So then that cancels very nicely for us, and here is my simplified complex fraction. So obviously this was a lot of work, in that like literally I had to write a lot of work on the page to get to this accurately. So we want to be a student A here, right? But it's definitely the same steps we did as we did up here for our numeric example. So it's not hard, it is time consuming, however. It would be good here to note that what we did to finally simplify this is we factored out a -1 to simplify this. But other than that, there is no trick to this. It's just step-by-step simplification. Now, you may be wondering why in the world would I want to do this? It's a lot of work, and we're just like kind of playing around with symbols here. And there's a couple answers to that. The most important one for me is that it allows us to tackle harder limits problems. That's something we've been working on throughout this course, right? So notice I have a limit here. Remember, my goal for a limit is to plug in that 3, but I can't plug in that 3 until I cancel this term out of the denominator, because my denominator cannot be 0. So I'm going to use the same strategies we used previously. So I'll get a common denominator on top. Here I'm going to rewrite my limit statement every time until I actually substitute. But I am going to be a little bit quicker with my algebra work. So I went ahead and I subtracted my numerators, wrote it over my common denominator right away. And notice there's nothing more I can do. I can rewrite it maybe. So dividing by x minus 3 is the same as multiplying times 1 over x minus 3. But I seem to be kind of stuck because I still have this x minus 3 in the denominator that keeps me from plugging in my limit. Well, notice what I can do is I can use the same trick as we used in the previous problem here. And I can factor out my -1, rewrite it as x minus 3 over 3x times x minus 3. And then my limit, or my factor cancels, allowing me to take the limit. So nothing left over is a -1 over 3x, and then I'm plugging in 3 to get -1 over 9. So notice this trick that we introduced in the previous page, super useful for taking this limit that we couldn't have taken before. Let's try one last example that's a little bit scarier looking, but uses the same skills. So I'm using the opposite denominators to make a common denominator, and I'm going to go ahead and distribute and add right away. Make sure you're distributing this -1 through. So I would get 2x squared plus 8x minus x squared plus 12 all over x times x squared minus 12 all over again x plus 6. And we want the limit as x approaches -6 of all that. So notice we still can't plug it in until we've canceled out this -6 down here. Okay. I notice I have some like terms I can combine on top. It is super easy, by the way, to make a mistake as you recopy all of your steps. That's why it's important to be a student A. This is actually my second take here because I miscopied one step right at the beginning and had to start all over because my signs were wrong. Okay, what I notice is I can factor the top here. So the top is equal to x plus 6 times x plus 2. X times x squared minus 12 stays the same on the bottom. And then instead of writing this x plus 6 as the denominator, I'm going to write it as just multiplication now. So I'm multiplying times 1 over x plus 6. And the reason I wrote it that way, it should be obvious, so I can cancel that out. And then my limit is suddenly much simpler, and that was what was keeping me from taking the limit. So my limit now is going to be the limit as x approaches -6 of x plus 2 over x times x squared is 12. So then I can plug it in. So we have a negative over a negative, which is a positive, and then when I divide out that 4 on top and bottom, I'm just left with 1 over 36. So there's my solution here. So notice with our new complex fractions techniques, we're able to tackle some problems we definitely couldn't have handled before. And you're going to fill up big pages worth of work, and everybody's going to be very impressed with you.